Hello everyone, this is an introduction to complex numbers for the course Math 119 at QCC. Okay, so the next topic that I want to cover is complex numbers. So you kind of already covered this before when you had to solve quadratic equations. So we're just going back a little bit to that, okay? Remember that the imaginary number I is defined as the square root of -1. Now, if I, which is a complex number, is the square root of -1, right? Remember, this is not a real number because there is no square root of negative numbers that are real numbers. Then is a different category of numbers which we call complex number. So I, the imaginary number, is the square root of -1. So if you raise both sides to the second power, of course, you get the I squared equals -1, because we saw before that the exponent 2 cancels the square root, so the result there on the right side is going to be just -1. So the important thing here is obviously the definition, but also I squared is a real number. Though I is not a real number, when you square I, the result is a real number, right? So keep in mind that the square of I, the imaginary number, is -1. So while you had to solve quadratic equation, most of likely that was when you have the square root, you have to evaluate the square root in the quadratic formula. And inside that square root, which we call the discriminant, the result of the expression of the quadratic formula, which is the discriminant, if that is negative, it means that your solution is going to be a complex number. So here's an example. So we can rewrite the expression square root of -7 as a multiple of I. So we wanted to rewrite this. So instead of having the square root of a negative number, we're going to write something with I. Now, the key point here is that we have a multiplication property, a product property for the square root. So if you separate 7 from the negative sign, which is the same thing as taking 7 multiplying -1, we know that we can separate the square root like this for the multiplication. Now, square root of 7 is a real number. Actually, it's irrational number, but it is a real number. But square root of -1 is I. So the answer here in terms of I is square root of 7, which is already simplified, times I. Now let's see another example like this. So let's take a look at the square root of -9. The square root of -9, again, I want to separate 9 from the negative sign, and the way we do that is by using the multiplication of 9 times -1. Now we can also split the square root because of the multiplication. Now, the square root of 9 is 3, so you have 3 times, and I is the square root of -1. So the result here is 3i. Okay, one more example. Let's take a look at the square root of -24. Again, let me separate 24 from the negative sign by writing 24 minus times -1. Now, I will have to simplify also square root of 24. So remember, if you separate here square root of 24 times square root of -1, which is I, 24 can be simplified. Remember, if you can rewrite what's inside the square root where there is a perfect square, because index is 2, so you want to look at perfect square, it means you can simplify, and you must simplify. Now, the simplification for the square root of 24 is 4 times 6, right? 4 is a perfect square, 6 is not, but that is the best I can do in terms to remove something from inside that square root. Now, this is I. I'm already writing I there. So again, if I split one more time, I have square root of 4 times square root of 6 times I. So the result is 2 square root of 6I. The square root of 6 is already simplified. Even though we can rewrite 6 as 2 times 3, there is no perfect squares as 2 and 3, right? The prime numbers. So it means this is already a simplified form of the answer. Now, as I mentioned above, is that I is what we call a complex number. It's not a real number because there's no square roots of -1 that are real numbers, and I is exactly that. But I is in the category of what we call complex numbers. Complex numbers are things that we can write in this form, right? So you have a number, which is a real number, plus minus a number times the imaginary number I. So again, either A and B, they both real numbers. So A and B are real numbers. But I, we know it's not. But if you can write your number is form, it means we can call it a complex number. Okay. So for example, here we see that this is a real number, 0.5 is a real number, plus 3i. So 3 or positive 3 is also a real number. So this number definitely is a complex number. As you see, is the same form a plus bi above. Now, here's another number, negative 10i. Now, I don't see the a plus b I form, but if I could express where I have a and b as real numbers and then followed by I, then it's still going to be a complex number. I can rewrite this number as 0 minus 10i, or you can write as 0 plus negative 10i. But you can see here that in this case, both 0 and negative 10 are real numbers. And because I can represent the number negative 10i in that form, it means that this number is a complex number. Just to move a little bit away from that, if you have any real number, let's say 5, 5, which is a real number, is also a complex number because we can write 5 as 5 plus 0 times I. So 5, which is a real number, is a complex number, right? So meaning if any real number can be written as real number plus 0 times I and it becomes complex, we know that all real numbers are complex numbers. But since I is not a real number, it means that not all complex numbers are real. So from real to complex numbers, yes, but from complex number to reals, not always. Basically, the set of real numbers sits inside the complex number, which is a much bigger set. So here are the real numbers. But there are things that are not real numbers, which is complex numbers. Okay, so the real numbers are inside a much larger set of numbers called complex numbers. Okay, so that's the point there. Okay, so what we want to quickly is to cover operations with complex numbers. Now, a plus bi looks like what we call polynomial, right? So if you think of I, which is not, it's not a variable, it is a fixed number. I is the square root of -1, it's not a variable. But if you look at I as if it were a variable, it looks like a polynomial. It's not a polynomial, but it looks like a polynomial, meaning we can perform the operations with the complex number as if they were polynomials. So if you are adding polynomials, you combine like terms. For complex numbers, you also combine like terms. The same thing goes for the subtraction. You also combine like terms. Multiplication, you have it first to distribute and then you combine like terms. For the division, though, we use something that we did before with the square root, which is conjugates, and we're going to cover that soon as well. Okay, so let's start with the addition subtraction that we see here. I have the complex number 6 plus 3i, and I want to add to the complex number -5 plus I. So I'm adding two complex numbers. So the parentheses are there to say, hey, this is one complex number, and I'm going to add it to this other complex number. As a polynomial, the way we do the operation of addition subtraction is first remove the parentheses out of the, and then look at the like terms. You remove the parentheses the same way you do for the polynomials. Now, if the parenthesis is preceded by a positive sign, nothing changes inside, you just remove the parentheses. But if it is preceded in front of it, there is a negative sign, you have to distribute that sign, which is going to change all the signs inside the parenthesis, and then you remove that parenthesis. So first step, remove parentheses. Now, There is an invisible plus in front of this parenthesis, so you just remove, nothing changes. So we have 6 plus 3i. And also there's a positive sign in front of the other parent, so you can just remove the parents without changing anything. Now we're going to look like terms. So like terms are things that have the same kind of format. So there are numbers, regular numbers, and there are terms that have I. So we're going to combine the terms with I, and we're going to combine the regular numbers. Now 6 minus 5 is 1. And for I, you take the coefficient, the numbers in front of I, and combine them. So we have positive 3 with invisible positive 1, right? Here there's an invisible positive 1. So positive 3 plus 1, positive 4. So positive 4i. Notice that your answer must be put in the form a plus bi. That's always something that's going to be required to write the answer for complex numbers. If you write the other way around, it's correct. It's just not in the form that usually is what's considered the standard, and especially for web work, it's going to definitely ask you first A plus B. Okay, so just keep that in mind. Okay, now for the subtraction, it's similar to the addition. If there is a plus in front of parentheses, just remove parentheses without changing anything. But if there is a minus in front of parentheses, to remove the parentheses, you must change everything inside the parentheses by changing the signs, right? You flip the signs, the plus and minuses. Okay, so here we have 7 plus 9i minus 2 plus 12i. So it's a subtraction of two complex numbers. The first parenthesis is preceded by the invisible plus, so we know that nothing needs to be changed, just remove the parentheses. So it's 7 plus 9i. Now here we have a negative sign in front of the parenthesis, so meaning the 2 becomes negative and 12i becomes also negative. You must switch the signs. So minus 2 minus 12i. Okay, so notice not the same thing. Now we're going to combine like terms. So we take 7 with negative 2. The result is 5. And we take positive 9i with negative 12i. So 9 minus 12 is negative 3. So negative 3i. Okay, and also is again in the form a plus bi, right? So there's the real part and then there's the imaginary part second. For the multiplication, again, similar to polynomials, first apply the distributive property, you distribute, right? So here we have two complex numbers in the multiplication. So we're going to multiply the complex number 4 minus 3i times the complex number 2 minus 5i. So first let's distribute. So we multiply first 4 and 2. So the result is 8. We multiply 4 and negative 5i. So negative 20i. And then we take negative 3i multiplies positive 2, negative 6i. And then we take negative 3i with negative 5i, positive 15i squared. Remember, I squared is negative 1. Because your answer must be in the form a plus bi, there is no I squared in this form. So because we can replace negative 1 with the I squared, that is taken care by that. So notice also that in this case, we have two like terms, and this is the same thing as negative 1. Okay, so now let's do that. So we have 8. Combine the like terms, negative 20i minus 6i, that's negative 26i. And then you have 15 times negative 1, which is negative 15. And again, with the replacement of I squared with negative 1, I have two like terms. So I'm going to combine 8 with negative 15. The result is negative 7, followed by the term negative 26i. Okay, so the key point here is that for the multiplication, most likely you're going to end up with something I squared. So just change that I square with negative 1. Okay, so next problem, also multiplication, but notice that like we had for the square root problems with binomials in the square root, they are almost the same. The only difference is the plus and minus sign in front of the imaginary part, right? So if you have a plus bi, the conjugate of that is a minus bi. So notice that I'm changing the sign, right? In the standard form of the complex number, I'm changing the sign in front of the term that has I. Now, this is the case for this. The two things are conjugate of it, right? Of each other. So if I do the multiplication with conjugates, so let's start here with 5 times 5, which is 25. And then I have 5 times 6i, positive 30i. And then I have negative 6i times 5, negative 30i. And then negative 6i times positive 6i, so negative 36i squared. When you look at the like terms in the middle, they have opposite signs because of that. And because they have opposite signs, they cancel each other. So then this is 25 minus 36, and I squared is negative 1. So when you multiply negative 36 with negative 1, you get positive 36. So the result is 6 to 1. If you look at this, there is no more I. It's still a complex number because it's 6 to 1 plus 0i, right? It's still a complex number. But when you write just 6 to 1, notice that there is no I. And that is a key point for the conjugates, like we did for the square root, which was to remove the square root from the expression. This works here to remove I from the expressions within the complex numbers. We use conjugates for the square root before in the division. Right now we're using this for the complex numbers. Because when you do the division here, these two numbers, right? So there is the numerator, which is 8 plus 3i, is a complex number. You're going to divide that complex number by negative 2 minus 5i, which is also a complex number. So it's a division of two complex numbers. The answer must be a plus bi, meaning I here is not being divided by anything. It's just I. It may be that this number a or this number b are fraction, but they are just part of the expression, not dividing I. Right here in the division we're going to do, there is a division that divides I, and there is I also in the denominator. So basically the key idea is that what if you remove I from the denominator and then becomes just a regular expression that the way I want, a plus bi. So that's what we're going to do. And in order to do that, again, you need to use the conjugate of the denominator. Denominator is what you want to remove I from, right? So let me rewrite this expression. So the expression is 8 plus 3i divided by negative 2 minus 5i. So we're going to do this division now. And again, I want to use conjugate. Multiply top and bottom by the conjugate of the denominator. The conjugate of the denominator is minus 2 plus 5i. Notice that I change from negative 5i plus 5i, but you need to do the same thing top and bottom. Let me repeat that on the top. Okay? By multiplying top and bottom is like multiplying the whole thing that you had before by 1, because this division in red equals to 1. And multiplying by 1 is not like you're changing the value. You just change how it looks, but not the value of the expression. So now we're going to do the multiplication, right? So you have to multiply numerators and you have to multiply denominators. For the numerators, we have 8 times negative 2, so that is negative 16. We have 8 times 5i, so we have 40i. We have 3i times negative 2, so negative 6i. And we have 3i times positive 5i, which is 15i squared. So this is just the numerator, the multiplication in the numerator. Now let's do the multiplication in the denominator. Remember, they are conjugates. So my expectation that when I write the final answer, there is no more I in the denominator. So we have, then let me try, I'm not going to write arrows there, but I have -2 times -2, +4. I have -2 times +5i, so -10i. I have -5i times -2, +10i. -5i times +5i, so -25i squared. Again, I squared is -1. So we're going to replace that with -1. I have like terms in the numerator, so we're going to combine these two. We're going to combine these two, which is basically a cancellation because the same thing, positive and negative, cancel each other. So the result is -16. Now 40 minus 6 is 34i, positive 34i. And then 15 is multiplied by -1, which is I squared. On the bottom, after canceling the middle terms there, I have 4 minus 25 times -1. Now let's simplify a little bit more the expression. So what we get then is -16 plus 34i. Now we have -15. On the bottom, I have 4 plus 25. Okay, so I still can combine like terms here. They are just regular numbers. The numbers in the denominator also can be combined. So the result, oops, denominator is 29. The numerator combine -16 with -15, we get -31 plus 34i. Remember, the answer has to be a plus bi. So if you separate the fraction, right, 29 divide both -31 and 34. So if you write like this, minus 31 over 29 plus 34 over 29 times I, that is equivalent to this form, right? Because this is like my A number and this is my B number, so A plus B I, okay? So you kind of have to split. So and the way we remove denominators with the division of complex numbers is by actually multiplying the conjugate top and bottom. And then you can split in the last step the fraction if you still have a fraction, right? Because sometimes it's get denominator 1, so no more fraction. But if you split the fraction, then you get the form when necessary because it doesn't need to have a denominator on the bottom of I, basically. Okay. So the answer, just confirm, is -31 over 29 plus 34 over 29. Okay, so we kind of went over all 4 operations with complex numbers. Notice that there's not much of new stuff really with the operations. The only new thing is the fact that you now know that I squared is going to replace it in certain operations by -1. That's something that you must remember. And let's see this also in this example here, which is the function notation. Okay, so notice that we're going to find the function f applied to the complex number 2 minus I when the function f of x is x squared plus 4x minus 1. And the answer must be put in the form a plus bi. Okay, so you have a function. The input of the function is the complex number 2 minus I, right? So this is the input. So it's going to replace x. Once you replace x, it's basically doing operations with complex numbers. So let's do that. So f of 2 minus I. So we're going to square the number 2 minus I and then add 4 times the number 2 minus I and then minus 1. All right, so f of 2 minus I. Notice that we have to perform the square. of the complex number, and the square means repeated multiplication, right? So you take 2 minus I and multiply 2 minus I. So we're going to have to distribute. Here I can already distribute, so that is plus 8 minus, minus 4I, and then followed by negative 1. Now let's multiply this part. So I have 4 minus 2I minus 2I plus I squared, followed by 8 minus 4I minus 1. Let's combine like terms, and don't forget this is the same thing as negative 1. So the like terms we have are these guys with this, and we have numbers as well. Oops, I should actually write a different. So the numbers I'll put inside squares like this. You can combine the numbers. Okay, so if I combine the numbers, I have 4 plus 8, 12, minus 1, 11. And then combine the like terms with I. So we have minus 2 with minus 2, negative 4, with another negative 4 minus 8, so minus 8I. And I squared is negative 1, so I still have that there. And one more time I combine like terms. So the answer is 10 minus 8I. So f of 2 minus I is 10 minus 8I. Okay? Okay, so basically we cover some extra operations with the complex numbers. You already had an idea from before. And now you're just seeing a little bit more of these operations with complex numbers, just to emphasize a little bit more. They are important numbers, especially when it comes to the actually solving quadratic equation in our case. But again, it's not just for the quadratic equations. It can be applicable to other things as well.